Yes, so Srikal students, let's discuss lecture number 4, chapter 5, Mechanical Properties of Solids, class 11, Physics. Well, in today's lecture, we are going to discuss different types of modulus, coefficient of elasticity. So first is Young's modulus, represented by Y. What is Young's modulus? You see, students, we know we have different types of stresses. One is a stress. Let's say this is a uniform cross-section bar and we are applying tensile force on one end and tensile force on the ends. We are applying tensile force. As you can see, this force either tensile or compressive force, this is normal to the surface. So in this case the stress will also be normal, right? This normal stress divided by longitudinal strain. What is longitudinal strain? Under the effect of this tensile force, obviously this bar would be elongated. As this bar is elongated, the elongation is happening across the length, right? So that is longitudinal strain. Now Young's modulus is simply the ratio of normal stress by longitudinal strain. All right. Yes, students. Experimental observations show that for a given material, for most of the metals, the magnitude of strain produced is same whether the stress is tensile or compressive. What does that mean? Whether I am applying tensile force or compressive force, the amount of strain is same. What it means to say is that suppose I apply 10 kilonewton of tensile force and let's say the elongation is 1 mm. So for the same amount of compressive force also, the shortening in the length will also be 1 mm. Now the ratio of tensile or compressive stress, you see, tensile stress as well as compressive stress, both are known as normal stress to the longitudinal strain, is defined as Young's modulus and is denoted by Y. Very, very important parameter in design of materials. When we choose the material, Young's modulus. So students, can we understand what will be the unit of Young's modulus? Very simple. See, it will be stress by strain, right? Now, what is the unit for stress? The stress is Newton per meter square. Am I right? So, Newton per meter square divided by strain has no units. That's why the unit of Young's modulus will also be the unit of pressure, that is Pascal. All right, let's go further. Newton per meter square. Now, students, we want to do a numerical. Structural steel rod has a radius of 10 mm. It's a steel rod. When I say rod, it means it has cylindrical surfaces. Am I right? So we have cylindrical steel rod. The radius is 10 mm and length is 1 meter. 100 kilonewton force stretches it along its length. Calculate stress, elongation, and strain in the rod. Young's modulus of the steel is given. Uh, it's given. So we want to calculate all these things. So students, how we will do? All right. So once again. Yes. So see that students, this is the rod. All right. It has circular ends. The length is 1 meter. That is equal to 1000 mm. But let's keep it in meter only, 1 meter. Okay, radius is 10 mm. This radius, this is 10 mm. Okay, so what will be area of cross section? So area of cross section, now see, he says 100 kilonewton force stretches it along its length. Stretches it along its length, obviously the force will be applicable on this area. So stretching means it's a tensile force, and the magnitude of force is 100 kilonewton. All right. So now we want to calculate stress. So it's a normal stress. So normal stress is equal to deforming force, that is equal to the force applied, external force applied, divided by cross sectional area of the rod, right? So deforming force is 100 kilonewton, that is equal to 100 into 10 raised to power 3 newton, divided by cross sectional area is pi r square, so it will be 22 by 7 into the radius is 10 mm. You please convert into meter, so 10 mm divided by 1000 square, right? This will be the value for the stress once you calculate this. Once you calculate normal stress, then it says what is the elongation. Elongation is delta L. Directly we cannot calculate delta L. First we have to calculate the strain on the rod. So students, now comes Young's modulus. Young's modulus Y, as we have just learned in the previous slide, that Young's modulus is equal to normal stress divided by longitudinal strain. Am I right? So normal stress, let's say we are able to calculate from here. Okay. Divided by strain is delta L divided by L. Well, L is original length, that is 1 meter. Okay, that's great. So that means delta L by 1, or simply delta L, I put on the other side of equal to, would be equal to here the normal stress divided by Young's modulus. So simply find the value for this and divide this value by this value, which is given 2 into 10 raised to power 11. This is 10 raised to power 11. So you will get the delta L, right? That is elongation. So once you know the delta L, in this case, you can find out the strain, that is same as delta L, because strain is equal to delta L divided by L. L in this case is 1 meter. So strain and delta L will be same. The magnitude will be same. Units will be, obviously delta L has a unit of meter and strain does not have any unit, or you can say strain has a unit of mm divided by mm. That is equivalent to saying strain does not have units, it's dimensionless. All right. So now let's go further. Yes, students. Now we want to find out what is the Young's modulus of the material of a wire. So how we will do it? See, this is the experimental wire. This one right side, wire B, and wire A is reference wire. Well, there's a scale attached to this wire and vernier scale just to see the extension in the wire. Okay, vernier caliper, screw gauge, etc. The devices which can take very accurate measurements, right? With the respective least count. So now initially this one mass here and one mass here is placed. All right. Now whatever is the extension in this wire because of the room temperature, that will be compensated because both the wires are there. Okay. Initially they are having same length. Now we add more weight and more weight, more mass. So there'll be extension, right? So this extension, when two masses are there, obviously vernier caliper will give you some reading. When it will go down, so you can find the difference and that will give you extension in this wire, right? So extension in the wire means you are able to find out delta L. Now delta L divided by this length, right students, will give you the strain. Very simple. Once again, let me just write it. Yes. delta, the strain will be found as delta L divided by L. Delta L we can easily find from here, right? So we know the strain. Now we know that Young's modulus is equal to normal stress divided by longitudinal strain. Am I right? So how we will find normal stress? Normal stress is equal to what? Deforming force divided by cross-sectional area. The area perpendicular to this, the deforming force should occur, right? So deforming force is the weight of the extra masses. Am I right? So once you know the weight of extra masses multiplied by G will give you the weight, that mg force divided by area would be pi r square. The same vernier caliper can be used to find the diameter of the wire. Dividing diameter by 2 will give you radius, pi r square will be the cross-sectional area. Now this force divided by area will give you sigma n, and sigma n divided by this strain will give you the Young's modulus of the material of the wire. That's it. So this is how you can find Young's modulus for any material. Just convert that material. Most of the materials having Young's modulus, they are ductile, so they can be converted into wires. And then this experimental wire, you can easily find the Young's modulus. All right, students. Yes. So students, now comes the second type of coefficient of elasticity, that is shear modulus. It is also known as modulus of rigidity. Its value is less than Young's modulus, almost one third of Young's modulus. Why? All right. So now students, all right students, shear modulus or modulus of rigidity is G, and I said its value is always less than Young's modulus, almost one third of Young's modulus. Let's try to understand and define what is shear modulus. So students, let's say this is a material for which we want to find out the shear modulus. Its shear modulus is when we apply the force tangentially over this surface. This is the surface, right? And we applying force. Now this surface shears. Am I right? So this surface, from just say from uh, from this point A, it goes to this point A dash, right? Now A dash is my extension or whatever you call it, shifting, lateral shifting. Okay, so let's say this is equal to delta x, right? Now the corresponding shear strain would be equal to delta x divided by this length, that is 50 centimeter in this case. Okay, delta x divided by L is the shear strain, and that is also equal to this angle theta. Why? For small angles, students, theta is equal to tan theta. And in this right angle triangle A dash L, you can easily see tan theta is equal to A dash, that is opposite side divided by adjacent side, that is AL, and AL is length L. So because tan theta is equal to theta, so I can say theta is my shear strain. So shear strain is this delta x by L in this case. Now make sure students, this surface of the material or a specimen should be fixed. This is fixed, right? Okay. Now once we know shear strain, then if you are somehow able to find the shear stress. So students, shear stress is sigma s. So that is equal to shear force. This is the shear force divided by the area on which this shear force is occurring. Shear stress, then this shear stress divided by shear strain, would give you the shear modulus, or we call it modulus of rigidity. Okay, students, based upon what we learned, uh, I'm going to say the shear modulus or modulus of rigidity, and there is a question. So see this question. It's given here that it's a square slab of 50 centimeter. So if this is 50, this will also be 50 centimeter, right? Thickness is 10 centimeter. I'm going to say this thickness is 10 centimeter. Okay. Okay, fine. Subjected to shearing force on the narrower face, 9 into 10 raised to power 4 Newton. So this is the shear force. So I'll write here shear force is 9 into 10 raised to power 4 Newton. Okay. The lower edge is riveted to the floor. This lower edge is riveted, means it is fixed. How much will the upper edge uh, be displaced? Beautiful. So basically, we want to find out this displacement, that is delta x. Now, just now we studied, students, that shear strain, and that is equal, shear strain is delta x divided by any student. Just now we studied, you remember? Shear strain is delta x divided by this length. So this length is, in this case, 50 centimeter, right? So 50 centimeter is, we can say, 0.5 meter. So this is the shear strain. And let's calculate shear stress. Shear stress is shearing force. Shearing force is 9 into 10 raised to power 4 Newton, right, divided by the area. So area is, you see, 50 into 10. 50 into 10, so that is 0.5 into 0.1 meter square. Am I right? So see, students, from here you are able to calculate the shear stress. From here you got the shear strain, only one variable, delta x. Okay, so now what is shear moduli? Shear moduli G, or shear moduli, or you can say modulus of rigidity. G is equal to shear stress divided by shear strain. Am I right? So G already we know for lead. It's a lead slab, that is 5.6 into 5.6 gigapascal. You remember? That is 10 raised to power 9 Newton per meter square. So this is equal to shear stress. Shear stress is 9 into 10 raised to power 4 divided by 0.1 into 0.1. Sorry, 0.5 into 0.1 whole divided by the shear strain, that is delta x divided by 0.5. So see, students, everything is given. This will help us to find out the value for delta x. This is how we will do this. So I would request students who are watching this online, YouTube, or my students, please do it and write down the answer in the comments after watching the video again. Yes, student. So we are done with the number one, Young's modulus. Yes, students. We are done with Young's modulus. Why? Then we are done with the shear modulus or modulus of rigidity. And now we are going to discuss bulk modulus. All right, the third one. These are three types of modulus. Okay, we are normally come across in the design of materials. Very, very important topic. Bulk modulus. So let's go, students. Let's go further. Let's see what is bulk modulus. Okay. So see that, students, we have seen that when a body bulk modulus is students normally defined when there is a change in the volume. Once again, when there is change in the volume. Okay. So you see that, students. Yeah. So when the body is submerged in a fluid, one second, I'm sorry. When a body is submerged in a fluid, it undergoes hydraulic stress. What is this hydraulic stress, students? So it is equal in magnitude of hydraulic pressure. So this leads to decrease in the volume of the body. Okay, let's say this is a this some fluid in this under high pressure, and in this fluid there's some body. So as because the forces are exerting on this body from all the directions, am I right, in the fluid, so it will go volumetric change. There'll be some delta V. Delta V is change in volume. Let's say V is the initial volume and V dash is the final volume. So delta V would be equal to V dash minus V. So it will be negative. Obviously it will be negative. All right, students. So uh, delta V we know. Now delta V divided by original volume V will give you volumetric strain, right? This is volumetric strain. We had longitudinal strain, the extension or compression along the length, along this, and then this is what longitudinal strain. And then we had shear strain. Shear strain is, this is the body, it becomes like this when I apply this force. All right, this delta x divided by this length is the what we call is shear strain. And the third one is volumetric strain. So volumetric strain is delta V by V, and that is always negative. So once we know volumetric strain, and then students, once we know the hydraulic stress, okay, what is that? Hydraulic stress. Okay, so hydraulic stress divided by volumetric strain will give you bulk modulus. Okay, students. So this is all about the materials. Hope you are able to see this. The ratio of hydraulic stress to corresponding hydraulic strain is bulk modulus. Wish you all the best, students. Thank you very much.